All right, if you run a high-performance RC, especially like a 110 scale buggy or truck, you've probably hit this wall. You get this awesome new brushless motor, you go to install it, and bam, the wires are just too short. They won't reach the ESC without pulling tight. Super frustrating. Now, you'd think, okay, easy fix, just add some wire. But hold on. How you bridge that gap? That's actually a huge deal for your whole system. Get it wrong, and you're looking at less power, maybe weird overheating, or even, yeah, that dreaded puff of magic smoke we all fear.
Exactly. And that's what this deep dive is all about. We're talking minimizing resistance, keeping things balanced in the system, pulling serious current. Our listener needs a solid, data-backed way to solve this, and they've nailed the three main options people consider. Those pre-made bullet plug extensions, doing it yourself by soldering new wires, or just taking it to a pro. So our mission today, cut through all the online noise and give you a clear way to figure out the best solution for you. We have to start with the why, the electrical basics that make this trickier than it looks.
Okay, yeah, let's dig into that foundation first, because I think like a lot of folks just assume those three motor wires, standard DC power, right? Simple stuff. What's really flowing through them?
Yeah, that's the big misconception, that an ESC is not just a switch, it's actually a pretty sophisticated DC to AC inverter. It takes the DC juice from your battery and uses these super fast switching transistors MOSFETs, usually to chop it up and rearrange it into three-phase AC power. Think of it like three separate, carefully timed power pulses going down those wires. That's what creates the rotating magnetic field inside the motor to make it spin. And here's the crucial part. Those three wires, they're designed as a matched set. The ESC absolutely relies on their electrical properties, especially length and resistance, being almost perfectly identical. If one wire is significantly different, maybe longer or has a bad connection, you throw off that timing. That's phase imbalance. And that causes nasty stuff like cogging. That's stuttering when you try to start smoothly.
Oh yeah, I hate cogging.
Right. Or even worse, it can completely lose sync at high speed, which can sometimes damage things.
Yeah.
So bottom line, whatever you do to one wire, you must do the exact same thing to the other two.
Okay, that makes sense. Now, before we even talk about how to extend them, let's tackle maybe the biggest safety issue I see debated online. Extending motor wires versus extending battery wires. Why is one okay and the other a potential disaster?
Ah, yes. This one's critical. The rule is really straightforward and honestly non-negotiable for safety or performance. It is generally safe to extend the wires between the ESC and the motor that's the AC side we just talked about. It is extremely risky, potentially catastrophic, to significantly extend the wires between the ESC and the battery, the DC input side. Don't do it.
Okay, why? What's the danger on the battery side?
Inductance. It all comes down to inductance. When you make those battery wires longer, you significantly increase the inductance of that part of the circuit. Now think of the capacitors right inside the ESC on the input side. They're like little electronic shock absorbers smoothing out the power. But that added inductance from longer battery wires, it fights against the super fast current changes the ESC needs, creating these huge voltage spikes right at the ESC's input.
Ouch.
Yeah, exactly. These spikes just hammer those input capacitors. They overheat, they bulge, they fail. And that's your magic smoke event 9 times out of 10.
Yeah.
But the motor side, the AC side, it's already a high inductance environment because of the motor windings themselves. Adding a bit more wire length there doesn't stress the ESC in the same dangerous way.
Got it. So stick to extending the AC side motor wires only. But even then, we're still fighting the ultimate performance killer. Electrical resistance. We want power, not heat.
Precisely. Resistance is the enemy here. It's just wasted energy turned directly into heat. And there are 4 main places it creeps in. First, wire length itself. Longer wire, more resistance, simple physics. Second, wire gauge. Thinner wire, meaning a higher AWG number, confusingly has higher resistance. Third, connectors. Every single plug, every bullet connector adds contact resistance where the metal parts touch. And fourth, maybe the sneakiest one, bad solder joints. Those infamous cold joints are major resistance points.
And what does this resistance actually do to performance, like tangibly?
Well, it hits you in 2 main ways. First is voltage drop. When you punch the throttle and pull high current, that resistance causes the voltage actually reaching the motor to sag. Less voltage means less power, less speed, sluggish acceleration. Second, and arguably worse, is the heat. Remember the physics formula. Power loss equals current squared times resistance. I2 times ID8.
Oh, squared.
Yeah, that squared term is the killer. It means if your setup pulls twice the current under load, you generate 4 times the waste heat due to that resistance. And that heat cooks your electronics, makes your ESC hit thermal shutdown sooner, shortens your run times, everything bad. Every tiny fraction of an ohm, every milliohm, really does matter in these high-power systems.
Okay, super clear. Resistance bad. Heat bad. Let's pivot to the solutions. Method 1. Bullet connector extensions. This is the easy button, the plug-and-play approach. If someone goes this route, what separates a good extension from, cheap junk that's just asking for trouble?
Quality is everything here. You absolutely need extensions made with high strand count copper wire. Flexibility matters. And the insulation. It has to be high-temperature silicone. Forget PVC. Silicone stays flexible and won't melt when things get hot nearby. PVC gets stiff, brittle, and can melt much easier.
Okay, silicone insulation. What about the plugs themselves?
Gold-plated, non-negotiable. Gold resists corrosion and oxidation, which keeps that contact resistance low over time. Cheap plating wears off, copper oxidizes, resistance climbs. And look for the connector style. Those split bullets, or the ones that look like little crowns, sometimes called castle style, they provide better mechanical grip and maintain spring pressure for a solid connection.
Makes sense. The advantages are obvious, right? Super easy, takes seconds. Modular, easy to swap motors or ESCs. Reversible if you change your mind. Maybe even acts like a fuse in a crash, pulling apart instead of ripping wires out.
All true. Convenience is high.
But we just hammered on resistance. What's the big electrical downside here? The penalty we pay for that convenience?
It's exactly what you think. The resistance penalty. Think about it. A direct connection from the ESC wire to the motor wire has essentially one connection point per phase. When you add an extension, you introduce 2 more connection points per wire, where the ESC wire plugs into the extension and where the extension plugs into the motor wire.
Ah, so you've doubled the number of spots where contact resistance can happen.
Exactly. You've fundamentally doubled the potential for resistance right there at the plugs. Remember, every connector adds resistance. That's energy lost as heat, right where those bullets connect.
Are there other risks besides just the baseline resistance?
Definitely. Vibration is a big one in RC, especially off-road. Those plugs can vibrate slightly, maybe work themselves loose over time. That can cause intermittent connection issues, stuttering, loss of power under load. And like I said, if you cheap out on the extensions and the plating is poor, corrosion becomes a real factor, especially if you run in damp conditions. Oxidation equals higher resistance, equals more heat.
Okay, so let's say someone understands the resistance penalty, but they still value the convenience. What are the absolute must-do best practices to make this method as reliable as possible?
Okay, 3 key things. First, wire gauge. You need to match, or even better, use a thicker wire gauge for the extension than what's on your motor. Remember, thicker wire means a lower AWG number. So if your motor has 12 AWG wires, use 12 AWG or ideally 10 AWG extensions. Never go thinner.
Got it. Lower AWG number is thicker, less resistance. What's next?
Second, connector size. For a 1 in 10 scale, 4mm bullet connectors are the absolute bare minimum. Honestly, for anything reasonably high power, you should really be looking at 5mm, 5.5mm, or even 6.5mm bullets. They handle more current with less resistance and heat.
Bigger is better for current handling. Makes sense. And the third thing?
The cheapest insurance you can buy, heat shrink tubing. Once you plug the extension bullet into the motor or ESC bullet, slide a piece of heat shrink tubing over that entire connection, covering both sides of the plug pair, and shrink it down.
Ah, so it holds them together mechanically.
Exactly. It provides mechanical security, stops them from vibrating apart, keeps dirt out a bit better, and just generally makes the connection much more robust, especially for bumpy off-road running. Don't skip this step with extensions.
All right, solid advice for the plug-in route. Let's shift gears to method 2, DIY soldering. This gets talked about as the ultimate performance option. If extensions add resistance points, why is a proper solder joint considered electrically superior?
It's because a good solder joint isn't really a connection in the same way a plug is. It's a metallurgical bond. When done right, the solder flows between and fuses with the copper strands of both wires, creating a single, continuous, seamless path for electricity. There's no physical gap, no reliance on spring pressure like a bullet connector.
So theoretically, almost zero added resistance compared to a continuous wire?
Theoretically, yes. Very, very close to zero added resistance. Now, some industries, like aerospace, prefer specialized crimping for vibration resistance, but that requires incredibly precise, expensive tooling most hobbyists don't have. For our purposes in REC, a well-made, properly strain-relieved solder splice is the lowest resistance, highest current handling, and frankly most durable connection you can make yourself.
Okay, sounds like the holy grail.
Okay.
I know so many people, myself included back in the day, who've absolutely wrecked expensive parts trying to solder thick wires without the right gear or technique. What are the real demands here? That little $15 pencil iron from the hardware store isn't going to cut it, is it?
Oh, absolutely not. Trying to solder heavy-gauge RC wires with an underpowered iron is probably the #1 cause of DIY damage. You need thermal mass and temperature control. That means minimum a 60-watt temperature-controlled soldering station, maybe even 80 or 100 watts for really thick wires or big connectors.
And the tip matters too, right?
Hugely. You need a large chisel tip, not a tiny pointy one. That big tip holds heat and transfers it quickly into the thick copper wire. If your iron is too weak or the tip too small, you end up holding the iron on the wire forever.
And melting the insulation on the motor or ESC right next to the joint. Been there.
Exactly. You also need good quality solder. 6040 or 6337 kin lead rosin core is still generally preferred for ease of use and reliability in this application. And don't be shy with extra flux. Liquid or paste flux is critical for getting the solder to flow properly into the wire strands.
Let's talk technique. What's the goal? How do you avoid that dreaded cold joint that looks okay but causes massive problems?
The perfect joint is bright, shiny, and smooth. It should look like the solder flowed into the wire, not just blobbed onto the surface. The mistake people make the cold joint happens when the solder melts. But the wire itself isn't hot enough for the solder to actually bond with the copper. It looks dull, gray, maybe lumpy or crystalline.
And that's bad because
Because it creates a super high resistance point right there.
under.
Under load, that cold joint can get incredibly hot enough to melt insulation, desolder itself, or even potentially cause a fire. The key is, heat the wire with the iron, then touch the solder to the hot wire and let the wire melt the solder, wicking it into the joint. Don't just melt solder onto the iron and dab it on.
Heat the work, not the solder. Got it. Now, before anyone grabs their iron and starts snipping wires, there's a huge danger zone, right? The one mistake that pretty much guarantees you've destroyed your motor.
Yes. This is the absolute critical warning, the red zone. This can instantly ruin a $100, $150, even $200 motor and will absolutely void your warranty. You must be extremely careful about where you cut the original motor wires, especially close to the motor can itself.
Why? What's back there?
Many higher-end motors don't just have those flexible silicone wires running all the way inside. Those flexible leads are often soldered internally to the actual winding wires, the magnet wire, that makes up the motor's electromagnets. Magnet wire is copper, but it's coated with a thin, tough enamel insulation. You cannot solder directly to that enamel.
So if you cut too short.
If you cut off the flexible silicone lead entirely and are left with just the stiff, enamel-coated magnet wire sticking out, you're in trouble. Getting that enamel off to solder requires scraping carefully or using extremely high heat, like 400 Celsius or 750 Fahrenheit, just to burn it off without damaging the winding. It's an expert-level repair, very easy to mess up permanently.
Okay, huge warning there. What's the rule then?
The non-negotiable rule is, check with the motor manufacturer before cutting any wires close to the motor can. Or, better yet, always aim to make your splice onto the existing flexible, silicone-insulated wire lead, leaving a safe distance from the motor end bell. Don't risk cutting into the magnet wire.
And even if you do a perfect soldering job on the silicone leads, you've still got to remember.
Warranty gone. Any modification like this, no matter how well done, universally voids the manufacturer's warranty on both the motor and usually the ESC if you modify its wires too. You're taking on that risk yourself.
Right. Okay, so DIY soldering offers top performance but requires skill, the right tools, maybe a $65 to $135 investment right there, and carries significant risk, including voiding warranties. What if someone looks at their shiny new $150 motor and just says, nope, my risk tolerance for messing this up is 0, or they just don't want to buy the tools?
That brings us perfectly to method 3, using a professional service. Taking it to your local hobby shop tech. And honestly, this can be a strategically excellent choice. It reframes the whole decision. Instead of focusing on saving maybe $30 on a service fee, you're prioritizing a guaranteed high-quality, zero-risk outcome. You're buying peace of mind and professional results.
So who should seriously consider this route? How do you decide if outsourcing is the smart move?
I think every hobbyist should ask themselves 3 quick questions. 1, do I really have the practice soldering skill for these thick wires? Be honest. 2, do I own the proper tools, that 60-plus watt temperature-controlled iron with the right tip? And 3, am I financially prepared and willing to just buy a new motor or ESC if my DIY attempt goes wrong? If the answer to any of those is no, then paying a professional is almost certainly the logical, safer, and potentially even cheaper path in the long run.
Let's break down that cost benefit then. What are we talking typically for a shop to do this, and how does that feel really stack up against the risk of a DIY failure?
Yeah, typically having a reputable hobby shop, solder extensions, or new leads onto your motor or ESC might cost somewhere in the range of, say, $20 to $50 plus maybe a few bucks for wire and connectors if needed.
Okay, so less than the cost of a good soldering station, usually.
Often, yes. And think about what that fee buys you. It's essentially an insurance policy against that $100 to $200 mistake of frying your component with a bad joint or too much heat. A good technician will deliver a connection that's electrically as good as or better than what most hobbyists can achieve themselves. It'll be reliable, low resistance, properly strain relieved, and often they'll even guarantee their work. You pay a bit upfront for a guaranteed race-ready result without any anxiety.
All right, that lays out the three methods really clearly. Let's try to synthesize this, bringing it all together for the listener facing this short wire problem. What's the final tailored recommendation? How do they choose based on their own situation?
Okay, let's recap the trade-offs real quick. Method 1, extensions. Low skill needed, low initial cost, easy to reverse, but you get that medium performance and reliability because of the added resistance points.
Right, the convenience penalty.
Method 2, DIY soldering. Needs high skill, needs the right tools, which cost money, not easily reversible, voids warranty, but it offers the highest potential performance and reliability if done perfectly. Big if there, carrying high risk of component damage.
High risk, high reward.
Maybe. Method 3, professional service. Low skill needed from you, medium upfront cost for the service fee, but delivers high performance and reliability with very, very low risk to your expensive components.
Okay, so based on that matrix, let's give some specific advice. What about the novice builder? Maybe someone who just wants to bash around and values convenience and avoiding headaches above all else.
For that person, absolutely start with high-quality bullet plug extensions. Get good ones, silicone wire, gold connectors, proper gauge, and definitely use that heat shrink over the connections. Yes, there's a small performance hit from the extra resistance, but honestly, for casual use or bashing, it's often negligible, and it completely avoids the risk of a costly DIY mistake. It's the smart, safe default choice for many people.
Okay. Now, what about the dedicated hobbyist? Maybe someone who isn't a pro racer but likes to tinker, values durability for long bash sessions, and is willing to accept the warranty risk to get a more robust setup.
For that person, yeah, the DIY solder splice is probably the target. However, the huge caveat is, do not make your expensive new motor the first thing you practice on. Get some scrap wire, the same gauge, get some connectors, and practice. Practice until you can consistently make those clean, shiny, strong joints every single time. Once you're confident, then tackle the real components. The long-term durability against vibration is a real plus here if you do it right.
Makes sense. Practice makes permanent, hopefully not permanently damaged. And finally, what about the serious racer? The person where every thousandth of a second counts, or the high-performance enthusiast who just demands the absolute maximum efficiency and reliability.
For the competitive racer or the absolute performance junkie, get it done professionally, period. In racing, every millionth of resistance does matter. It translates to heat, voltage drop, slightly less punch, slightly shorter run times. A professionally soldered connection guarantees the lowest possible resistance, done correctly and reliably. That small service fee is absolutely worth it to eliminate any chance of a connection failure costing you a race, or just to know you have the most efficient setup possible. It's performance insurance.
Excellent breakdown. So it really boils down to an honest assessment of your own skills, your budget for tools versus service, and how much risk you're comfortable taking with potentially expensive parts.
Exactly. The key takeaway is there isn't one single best answer. The optimal solution is the one that fits your specific situation, your skills, your budget, and your tolerance for risk.
Perfect. Well, we spent this whole deep dive focused laser sharp on resistance in that critical link between the motor and ESC and how to minimize it when extending wires. So resistance is the big bad guy, always stealing power and creating heat. What's maybe the next most common component, not wires, in a typical RC power system that a smart hobbyist should look at closely, maybe inspect or upgrade if they want to further maximize efficiency and keep temperatures down? Just something to think about as you look over your own setup.